Welcome to Chapter 2, focusing on UV visible spectroscopy. This technique examines how molecules absorb ultraviolet and visible light, causing electronic transitions. UV-vis is one of the most widely used analytical methods because it's simple, fast, and quantitative. We'll explore why some molecules are colorful, how electronic structure determines absorption, and how to use Beer-Lambert law for concentration measurements. Electronic transitions involve moving electrons between molecular orbitals. Four main transition types exist, ordered by decreasing energy. Sigma to sigma star requires far UV light and occurs in saturated compounds. N to sigma star involves lone pair electrons transitioning to antibonding orbitals. Pi to pi star transitions happen in unsaturated systems and often fall in the UV visible range. N to pi star transitions are the lowest energy and appear in compounds with both lone pairs and pi systems like carbonyls. Sigma to sigma star transitions require the highest energy, occurring around 150 nanometers in the vacuum UV region. This wavelength is absorbed by atmospheric oxygen, so standard UV-vis instruments cannot detect these transitions. Saturated hydrocarbons like methane, ethane, and cyclohexane only show sigma to sigma star absorptions, making them effectively transparent in routine UV-vis measurements. This is actually useful, since these compounds can serve as solvents. N to sigma star transitions occur when lone pair electrons on heteroatoms like oxygen or nitrogen are promoted to sigma antibonding orbitals. These appear at 180 to 220 nanometers. N to pi star transitions involve lone pairs moving to pi antibonding orbitals, occurring at longer wavelengths, 270 to 350 nanometers. The carbonyl group in acetone shows a characteristic N to pi star band at 280 nanometers. These transitions are generally weak with low molar absorptivity values, typically between 10 and 100. Conjugation dramatically affects UV-vis absorption. As the conjugated system extends, the HOMO-LUMO energy gap decreases, shifting absorption to longer wavelengths. Ethene absorbs at 171 nanometers, butadiene at 217 nanometers, and hexatriene at 258 nanometers. Beta-carotene with 11 conjugated double bonds absorbs at 450 nanometers in the visible region, appearing orange. This conjugation-color relationship explains why many natural pigments and synthetic dyes are highly conjugated molecules. Chromophores are functional groups responsible for light absorption, including carbon-carbon double bonds, carbonyls, azo groups, and aromatic rings. Oxychromes modify the absorption of chromophores without absorbing in the near UV or visible region themselves. Groups like hydroxyl, amino, and alkoxy cause bathochromic shifts, moving absorption to longer wavelengths. For example, adding an amino group to benzene shifts the lambda max from 254 to 280 nanometers. Understanding these effects helps predict and tune molecular absorption properties. The Beer-Lambert law is the foundation of quantitative UV-vis analysis. Absorbance equals epsilon times path length times concentration. Epsilon is the molar absorptivity, characteristic of each compound at each wavelength. Path length is typically 1 centimeter using standard cuvettes. The linear relationship between absorbance and concentration enables precise concentration measurements. For example, with epsilon of 15,000, a 1 centimeter path, and 0.05 millimolar concentration, the absorbance would be 0.75. A UV-vis spectrophotometer has 5 main components. Light sources include deuterium lamps for UV and tungsten lamps for visible light. The monochromator uses a prism or grating to select specific wavelengths. The sample compartment holds cuvettes containing reference and sample solutions. Detectors, either photomultiplier tubes or photodiode arrays, measure transmitted light intensity. Double beam instruments automatically compensate for solvent absorption by comparing sample and reference beams simultaneously. Talk plots are essential for determining semiconductor band gaps from UV-Vis data. When photon energy exceeds the band gap, electrons transition from valence to conduction band. The Talk equation relates absorption coefficient to photon energy, with the exponent n depending on transition type. N equals 2 for direct transitions and 1/2 for indirect. Plotting and extrapolating the linear region to the x-axis gives the band gap energy. This is crucial for solar cell and photocatalyst development. Chapter 2 covered UV-Vis spectroscopy essentials. We learned 4 electronic transition types and how conjugation causes red shifts. Chromophores absorb light while oxychromes modify absorption. Beer-Lambert law enables quantitative analysis through the A equals epsilon LC relationship. Talk plots determine semiconductor band gaps. In Chapter 3, we'll explore IR and FTIR spectroscopy, examining how molecular vibrations provide complementary structural information through different vibrational modes.